My name is Yuganis Varman Balan. My metric number is 143470. Today in this slide, I will be explaining about ferroelectric structural categories and structural change during phase transition. So just an overview, I'll be talking about four different structural categories and also structural change during phase transition. So the first structural category is corner sharing oxygen octahedra. So these are the five examples, which are perovskite, tungsten bronze, bismuth oxide, and also lithium niobate and tantalate. So what is an octahedra? So right here I have pasted a picture which looks like a two pyramid joined together. So this is an octahedra. So for a corner sharing oxygen octahedra, the oxygen will be at the vertices here or the corners. So here I've given an example, which is barium titanate, and here you can see the octahedra shape, whereby the oxygen is at the center, it is at the vertices or the corner. So what happens when electricity is passed through this structure? Once electric field is applied, the metal atoms are repelled and oxygen atoms are attracted. So when that occurs, the unit cell will start to expand and contract perpendicularly, which eventually produces the finite polarization. As for hydrogen bonded radical structural category, we have three different main examples, which is KDP, TS, and Rochelle salt. So mainly they have properties whereby they are soluble in water, but they have weak ferroelectricity, low Curie points, where Rochelle salt has two Curie temperatures at negative 18 degrees Celsius and 23 degrees Celsius. They also are known for having poor mechanical properties. So there are some of the advantages with this group, whereby KDP family crystals have good electro-optical and non-linear optical properties, and TGS family crystals have excellent pyroelectric properties. So these large crystals with high optical quality are easily grown in from their aqueous solution. And then next we have these two pictures of KDP and also TGS structures. So we're going to explain more on this. So for KDP, it is not ferroelectric at room temperature, but TGS is. And for KDP, its Curie temperature is negative 150 degrees Celsius, and TGS is at negative 49.7 degrees Celsius. So for KDP, it is a good electro-optic and non-linear optic property. It has good electro-optic and non-linear optic properties. And as for TGS, it has good pyroelectric properties for infrared detectors. And usually KDP is applied in electro-optic devices, high power pulse lasers, electro-optic modulator, and light wav devices. As for TGS, although they have the largest response sensitivity, but they get easily depolarized at room temperature due to low Curie temperature. Next, we have ferroelectric polymers. So, as the name suggests, the polymers, they have long chains of carbon atoms. So, they occur very naturally and they're not synthetic organic materials. So, usually they are bamboos, bone, skin, blood vessel, hair, and silk, as well as PVDF. So, so the polarization is induced from orienting the crystalline phase of polymer under high electric field. So, not only electric field can polarize these ferroelectric polymers, temperature can also affect the ferroelectric polarization. Next, we have PVDF structure from three different sites A, B, and C. This is right after it goes through a beta phase from alpha phase. So once about 60 degrees Celsius is applied onto this structure, it starts to stretch at 60 degrees Celsius from alpha film to beta phase. And due to this, it will give rise to spontaneous polarization. So the amount of beta space in PVDF film depends on the temperature and also the elongation. So in this structure, the hydrogen is positive and fluorine atoms are negatively charged. So as for ceramic polymer composite structure category, they are just basically a combination of ceramic and polymers. So here I've summarized it, whereby the properties of polymer and ceramics will be combined into a polymer ceramic composite, which will then have a combined and enhanced behavior. So usually this ceramic polymer composite will be made up of actic ceramic phase embedded in a passive polymer phase. So the composite is usually produced to optimize the most useful properties of two different phases that don't normally appear together. Their main applications are in aerophones and as transducers and medical transducers. So, for example, we have PVDF PZT composite film for transducer application. So in PZT piezoelectric, It has high dielectric constant, good electromechanical coupling. And if you were to composite that with PVDF, and PVDF has flexibility, a polymer, chemically inert, creep resistance, resistance to sunlight, you will eventually get a piezo polymer piezo ceramic composite, which has flexibility from PVDF and high piezoelectric properties from PZT. So that is what ceramic polymer composite does. Lastly, we're going to talk about structural change during phase transition. So I chose displacive type, and there's actually two different types, which is also order disorder. So in this slide, I'll only be talking about displacive type. So what is displacive type? So displacive type is basically when the structure gets displaced. Basically, the atoms or the ions gets displaced. So when ions in the structure get displaced, it will displace itself from equilibrium slightly. So when this happens, the force from the local electric field due to the ions in the crystal increases faster than like elastic restoring force. So imagine all these ions, it gets stretched out. So the force is created, basically electric force is created, that will eventually stretch this structure, but it cannot go back to its original position. It cannot restore its forces. So basically, it cannot go back to its original position, and an asymmetrical shift in the equilibrium of ion will happen, which will eventually give rise to the permanent dipole moment. So that is what a displacive type does. So these are for barium titanate. So for barium titanate, we have two different TC, Curie temperature. So when the Curie temperature is below TC, when the temperature is at below Curie temperature, the barium titanate's ion will start to shift. Now, when the ions start to shift, the center of positive and negative charges deviate from equilibrium position. Now, as we've seen earlier, when the charges start to deviate from equilibrium position, we have a net dipole moment, and then consequently, we have a polar state in the system. Now, let's say barium titanate is undergoes a temperature that is more than Tc. So the ions will attain equilibrium position, which is opposite to what we saw earlier, and the net dipole moment will not be present, therefore producing a non-polar state. So that is it from me. Thank you.